VSEPR theory. Hello, it's Medicosis Perfectionalis. Welcome back to my chemistry quick review playlist. In previous videos, we talked about the periodic table, periodic trends, the 4 quantum numbers, molecules, compounds, elements, bonds, chemical equations, polyatomic ions, etc., etc., etc. As for today, it's time for the VSEPR theory. What does VSEPR stand for? Valence shell electron pair repulsion. So the most important thing to understand about VSEPR is that electrons repel from one another. Electrons hate each other with vengeance. So electrons will try to stay as far away from one another as possible. The greater the repulsion, the greater the energy. And as you know, the greater the energy, the lower the stability. And nature does not like that because high energy means high maintenance. Energy wants something that is low energy and low maintenance, i.e. more stable. That's why VSEPR predicts that the molecular geometry will have the least repulsion possible, i.e. the most stable. And this phenomena will give us all kinds of geometrical shapes. Why? Because electrons hate each other and they're trying to stay apart from each other. I hope that you watch these videos in the Chemistry Quick Review playlist in order for maximum understanding and retention. Remember that valence electrons, i.e. electrons in the outermost shell, are either bonding pair, who make bonds, or lone pairs, not part of bonds. Look at this lovely thing right here. That's a covalent bond, which includes 2 shared or 2 bonding electrons. 2 electrons equal 1 pair of bonding electrons, 1 pair of shared electrons. But look at this. That's a lone pair. That's a lone pair, that's a lone pair, i.e. non-bonded pair. The bonding pair, the shared pair of electrons will give us covalent bond. If you just have 1 pair shared, you get 1 single covalent bond. If you have 2 pairs of electrons shared, that's a double bond. It's a covalent bond, of course. How about 3 pairs of shared electrons? You get a covalent triple bond. By the way, the single covalent bond is the longest and the weakest. Double bond is stronger and shorter than the single bond. However, triple bond is the shortest and the strongest. What do you mean by strongest? I mean it's the hardest to break. I mean it needs the most energy in order to break. Conversely, a single bond is the weakest, which means easiest to break, which means the least amount of energy is needed to break it. And if you have watched my biology or biochemistry playlist before, you will remember this. That's your DNA anti-parallel double helix, but look at the base pairing. Adenine pairs with thymine and guanine pairs with cytosine. Between A and T we have 2 hydrogen bonds, but between G and C we have 3. Which one do you think is more stable? Of course the 3. That's why my mnemonic was GC, stability. The same concept applies here. The triple bond is the most stable. Recall that the nucleus is positively charged, but the electrons are negatively charged. And that's why the negative electrons will repel one another, creating 3 types of repulsion forces. There is a repulsion between the bonding pair of electrons here and the bonding pair of electrons here. Recall that each covalent bond has 2 electrons here, so 1 shared or 1 bonded pair of electrons, and they will repel one another because they are negatively charged. The second type of repulsion is between this lone pair and this lone pair, so it's lone pair repulsion. And the third type is between a lone pair of electrons and a bonded pair of electrons. That's also repulsion. Repulsion forces exist whether you are a bent structure or a linear structure. And recall that we're trying to get the electrons as far away from one another as physically possible. VSEPR, valence shell electron pair repulsion. For dummies, electrons hate one another. Electrons repel each other. They try to stay as far away from one another as possible. The greater the repulsion, that's a force, the greater the energy, and the lower the stability. And that's why we're trying to get them with the least repulsion possible to make them more stable, because nature likes more stable states because they are easier to maintain. VSEPR predicts the geometry of individual molecules from the number of electron pairs around the central atom, as we'll discuss shortly. It's the number of electron groups around the central atom which determines the maximum separation between them due to repulsion. And this separation will give us an angle. So let's suppose that we have one central atom in the middle and two peripheral atoms. Okie dokie. Here is one single covalent bond and another single covalent bond, which means we have a pair of electrons here and a pair here. So how many pairs do we have? One pair and one pair equals two pairs. I mean two electron groups around the central atom. And when you have two groups or two atoms around the central, the angle is 180. Where did you get that number from? Easy. Remember, if we have a point in the center, we can make a circle around it and it will be 360 degrees. Divide this by the number of groups. 360 by 2 equals 180. And this shape is linear in 2 dimensions only, not 3D. Next, how about one central atom and 3 atoms around it, or 3 electron groups around it? Easy. 360 degrees divided by 3 equals 120. Are you 3-dimensional? No, not yet. Just still 2-dimensional. You can draw this shape on a piece of paper. Okay, 3 means trigonal planar. That's the geometry. How about having 4 atoms around the central atom? A doofus will say, easy medicosis, 360 divided by 4 is 90. But remember, 90 is not the best, because we're trying to get the electrons as far away from one another as possible. So 109.5 is more far away, more distant than 90 degrees. Of course, because it's a larger angle. Exactly, and that's why we need to organize ourselves in 3-dimensional structure, forming a tetrahedral. How about 5 groups or 5 atoms around the central atom? Well, this is trigonal bipyramidal. Think of 2 pyramids opposite to one another. The bases are touching and you have something smacking right through the middle. I can draw the structure on paper, but then imagine that there's an atom coming out of the paper and another atom going deep into the paper. Angles 90 and 120 degrees in 3-dimensional shape. How about 6 atoms or 6 groups around the central atoms? Then we have an octahedral and the angle is 90 degrees. All of that we have just discussed is the ideal angle. What do you mean? I mean, it's what happens when all the electron groups around the central atom are bonding pairs of electrons, not lone pair of electrons. If all of them are bonding pairs, you have ideal situations. But what if I have lone pairs of electrons? Then they will distort the angle. The actual angle will be lower than what you expected from this table. But why do I have angle distortion? I mean, why do I have reduction in the ideal angle, lower than expected? Because the lone pairs of electrons will push down on the bonding pair and reduce the angle. That's what we mean by angle distortion. Can you give me some concrete example to understand? Yes, of course. Think of ammonia, NH3. We have a central atom, that's nitrogen. And then we have 3 peripheral atoms. Here's one hydrogen, one hydrogen, one hydrogen. Here's a single covalent bond, a single covalent bond, and a single covalent bond. So 2 electrons are here, 2 electrons are here, 2 electrons are here, which means 6 electrons. Is that octet? No, it's not octet, which means we have a remaining lone pair of electrons here. Whenever you see a lone pair of electrons, you can bet the rent money. There will be angle distortion. There will be reduction in the ideal angle and it will be lower than expected. First, let's see how many did we expect before this nonsense happened. Here is one pair of shared electrons, another pair of shared electrons, a third pair of shared electrons, and one lone pair. So the total is 4 pairs of electrons, i.e. 4 groups. And when we have 4 groups, what's the angle that we expect? 109.5. That was the ideal, but did we find this ideal angle in nature? No, we actually found 107 degrees instead. Why is what we found lower than what we expect? Because of angle distortion, which reduces the ideal angle from 109.5 to 107. This was created by the lone pair of electrons. Worse, think of water, which has not just one lone pair, but 2 lone pairs of electrons. First, what was expected? Well, here is one group, one group, one group, one group. When you have 4 groups, what's the angle that you expect? 109.5 because I have 2 covalent bonds and 2 lone pairs, so I expected 109.5. I expected a tetrahedral. But is this the actual molecular shape? No, the actual molecular shape is bent. And instead of 109.5 degrees, we have 104.5. That's the real life bond in water. Why is the actual angle lower than the ideal angle? Because of angle distortion. Because of reduction in the angle, because of the lone pairs of electrons. And here is a pearl for the pros. The greater the number of lone pairs, the greater the reduction in the ideal angle, i.e. the smaller the angle. When I had no lone pairs, the angle was 109.5. When I had 1 lone pairs, the angle decreased to 107. When I had 2 lone pairs, the angle decreased even more to 104.5. Why doesn't your freaking professor explain it like this? Let's do it again. What is angle distortion? It's what happens due to the presence of lone pairs of electrons. Here I had 1 lone pair and 3 covalent. If you have 1 lone pair, you will distort the angle and it will be lower than you expected. You expected 109.5, but what you got was 107. Let's add another lone pair. Oh, I have more lone pairs, which means more distortion, which means a lower angle than I expected. The greater the number of lone pairs, the greater the reduction in the ideal angle, and the smaller the angle. Okay, medicosis, I got this. No, until you get a blank piece of paper and draw all of this from scratch with your own handwriting. Practice, practice, practice. By the way, you can download these lovely colorful notes from my website, medicosisperfectionalis.com. Please don't be fooled. There is a difference between electron domain geometry and molecule shape. When I say that I have 4 groups and therefore tetrahedral, you are referring to the domain geometry. It refers to any place where you have electrons, whether they are shared pairs of electrons or lone pairs of electrons. We don't care. So in water molecule, we had 4 electron domains, 2 lone pairs and 2 shared pairs. Total equals 4, so we expected the tetrahedral according to the geometry. But is this what we actually found the molecule shape of water to be? No, the actual shape of the molecule of water is bent. Why is this answer different than this answer? Because the molecule shape only cares about the effect of the lone pairs of electrons, not the electrons themselves. And that's why there is a big difference between the domain geometry and the molecule shape. These two may be identical if there are no lone pairs of electrons. If everything is shared, then everything will be like we expected. But since water has 2 lone pairs, the actual angle of the water was 104.5 instead of 109.5. It's the presence of the lone pair that gave me the bent structure. Which means whether or not you have lone pairs of electrons will determine the angle. So the angle cares about the absence or the presence of lone pairs of electrons. And if we have lone pairs of electrons, how many? Is it just 1 pair? Is it 2 pairs, etc.? And if we have a bent molecule shape, as in water, then this angle is between 90 and 120. In case of water, it was 104.5, which is greater than 90 degrees, but lower than 120 degrees. Let's answer the questions of the previous video. Keep watching because there are questions about VSEPR coming. Give me the electron configuration of the following neutral atoms. Please pause and try to answer this yourself. Let's do it together. Remember my mnemonic. SS, PES, PES, DPS, DPS, F, DPS, as in F me. Scandium is element number 21 in the periodic table, so we need 21 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. After the s, what do we have? 3d1. From low energy to high energy subshells. And then the next one, titanium. Similarly, but instead of 3d1, we have 3d2. How about vanadium? Very similar, and you end with 3d3. Stop right here and be very careful with freaking chromium, because look at this. It's not 4s2, 3d4, because 3d4 does not exist. We observe that for S1, 3d5 is the configuration, which means that chromium broke the Aufbau principle. What did Aufbau say? It said fill the low first. Aufbau, fill the low first. But we did not. We went for S1, 3d5. Why did this nonsense happen? Why did chromium broke the internet? Because it has been observed that having a half-filled D subshell is more stable than having a full S subshell. Next, manganese is easy because it just makes sense. Here is another question for you. In the compound below, what's the least electronegative element? Is it the carbon, the chlorine, the fluorine, the iodine, or the bromine? Let me know your answer in the comments. Can you draw the lowest dot structure for the following? We have 4 molecules and 1 compound. Here is another question. Do you expect the molecular shape of SCl2 to be bent? Yes or no? How about the molecular shape of SO2? Do you expect it to be bent? Yes or no? Let me know the answers to these questions in the comments. You'll find the answer key in the next video. If you found my videos to be helpful, please consider supporting the channel by buying me a coffee. Thank you so much in advance. Thank you for helping me help you. There are more than 1,500 educational videos on this channel, plus 300 premium videos that are only for my YouTube members who join the channel and chose the highest tier. Smash like, subscribe, hit the bell. Go to medicosisperfectionalis.com to download my notes, courses, and cases, or if you'd like me to personally tutor you. Be safe, stay happy, study hard. This is Medicosis Perfectionalis, where medicine and chemistry make perfect sense.